Hey, my name is Damien. I grew up in the North Shore in North Van, with the high school in North Van, and I want to talk a bit about my experience in undergrad I did engineering physics, and so I'll talk about that experience. I worked for a bit after, then I came back to grad school, so I'll talk about all of that and how I felt about the whole thing. So I also transferred. I transferred to Cap College. It was called Cap University now. Back then it was called Cap College. They have a first-year engineering transfer program, and it's exactly the same as first-year engineering here. So it was very, very, very easy for me to take courses there and come here. The class sizes were like 60 instead of a few hundred. Tuition was much cheaper, and you had so much more resources because it was smaller classes. It was excellent for the transfer from here. I had my first engineering project at Cap, and we had to make a car entirely out of wood that ran only on wooden or on rubber bands. And so me and a few buddies made this, and it worked really well. It went further than any other car in the program. So we had gears, and so we studied gears. We learned how to make gears, and we took advantage of it, and it worked out really, really well. I wish I could show you a video. It was cool. After that, in your first year of engineering, you decide, you get exposed to all different kinds of engineering at UC and other universities. You sort of are able to pick, based on the meetings you have with these people that come to talk, which engineering speaks to you the most. And I chose engineering physics because I liked building things. I always liked working with my hands and figuring out how things work, but I also liked physics, because physics explains a lot of things. It would be nice if I could understand what I was making, and if I could understand the physics behind the physics behind the designs I wanted to ultimately come up with. What I think is the coolest part about engineering physics is that in the second year you get to make a robot. You spend the entire summer designing your own robot that's supposed to do some course, and then at the end of the summer you have a bunch of people watching the robotics competition. And so my year had to, you just push on, and it has to find its way through some track and then rescue this little doll off the cliff. And so that's the robot that we made, and I made all of the electronics. That was my job. All those circuits, those are my circuits. And then that's it there. And we did really well here, and that's me full of excitement. We came in second place, but I was very happy. Another cool thing about engineering physics is they have a stellar co-op program. So these are internships where you work with the university and you write reports that they help you find these other jobs. And engineering physics is part of the science co-op program. And the science co-op program is very good. Almost everybody gets a job. So I had, my first job was in Nelson, actually. It's like 10 hours east of here. And I worked on these electronic components that test electronics for cars and trucks. Like, I don't know if you've been in a new Ford car, they've got all these LED lights. So this company makes all those LED lights and heated steering wheels, heated seats, flashing lights for trucks and stuff like that. I spent a summer working for a company that does traffic systems and street lighting, and I spent another summer here working in a lab that works on antennas and wireless systems. I had a fantastic co-op experience because I was able to taste all different kinds of engineering. The first one was sort of a company that manufactures its own electronics in-house, and they design all the electronics in-house. The second one was consulting, so it's a small number of people that bid on different projects. There's always different projects that you do, all different styles. You're not working on the same projects, the same products. It's always different, and you can become a partner. You can buy a share of that company, become an owner. That's completely different style than the electronics corporation was working for before. And then I also got a taste of research and seeing what that was like. So in the end of co-op, I really got a taste of all different kinds of engineering. In my third year, I made a gyroscopic computer mouse. This was a circuit that I designed, and then I built that, and it looked like that. Basically, the way a gyroscope works is that if you have some spinning disc, so like a top, for instance, with a spin, if you put a force on it, it responds to that by, it's called precession. If you see what happens, it tries to fight back and it turns as a result. And so what I did was I put these resistors, they change the resistance as you pinch it. And I just shoved it in the gyroscope, and then they were spinning really quickly, and then you could turn it, and as you turned it, the mouse would move on the screen. So I would point it at the screen, and I would move it around, and I could control the mouse on the screen. That was really cool. I mean, these are skills that I learned in co-op. I mean, it sounds kind of cocky to say. No one else in our program knew how to do these kinds of circuits. I learned how to do these circuits because of co-op, my experience at work taught me that. Once I was in my 4th and 5th year, my projects were physics-based projects. Me and 2 other guys in my program worked in the atomic, molecular, and optics lab. And we made this laser. Over 2 years, we designed it. Well, first we had a prototype that didn't work, so the second we designed this. And then we built it, and it's part of a larger system that we didn't design. And this larger system was used to cool atoms down to like a billionth of a degree above absolute zero. When certain gases get that cold, they have very strange properties. You've got phases like solid, liquid, and gas. Well, there's another phase that appears when you get that cold, called Bose-Einstein condensate. That's something that Einstein predicted. And then in the 90s, this guy called Carl Lyman got a Nobel Prize for it. He was here for a while, reforming the education of physics. That was a lot of fun. Once I graduated, I got into geophysics. I got a job at a company that uses these non-invasive techniques where you're not doing great for time. Where you're not digging to find out what's underground. I got hired because I knew a lot of electronics and programming computers, and my experience in co-op and my project experience in my undergrad put me in a very good position to help them out with a robot they were trying to build. Basically, after my interview, they wanted me to start right away because I had 1 month to help them finish a robot. And so this is me working on the robot, having fun in the mine, and standing. I mean, the first job that we had was to inspect this pipe that was like a kilometer inside this mountain. And so, because you can't go in the pipe, you have to make a robot to do it for you. And so, over the course of this month, and it turned out to be like a month and a half, me, the president of the company, and one other engineer, the 3 of us, were basically locked ourselves into a room, and we made this robot. It worked very well. Yes?
And you didn't leave the room?
Not even to eat or sleep. No. I also had a lot of other fun in geophysics that wasn't robotics based. When I wasn't making robots, I mean, these aren't pictures of me, these are off the website, but I was doing surveys just like this. Surveys where you put, you use dynamite to send shock waves through the Earth, and then as you find layers where the Earth has different densities, the shock waves bounce in different directions. And so if you have these microphones laid out on the surface of the Earth, or on the ground, and if you know where the dynamite came from, and you know the time delay, you know how long, at what time all your microphones got the echoes of the reflected waves, you know how deep the Earth was. So you can use physics to make a lot of money telling mines how much Earth they have. We also had surveys where we were in boats, and we used various other physics techniques, like if you measure the conductivity of the Earth, or of the ocean floor, you can tell if there's conductive materials like gold or copper there. And so if you, the company, I didn't work on this, but they have this patent on this device that sends electromagnetic fields in the water right over the surface of the ocean floor. And if you know that it's very conductive material, you know you have gold or copper. And so they can make a lot of money doing stuff like that as well. They can also tell you how much, you can use geophysics to know how much ice you have by putting electromagnetic waves, essentially making radar in the ice to know how much ice you have and looking at how the waves bounce off of the Earth at the bottom of the ice. Geophysics is a very interesting field. If you're interested in physics, I would consider geophysics. But at the end of that, I decided I wanted to go to grad school and I wanted to get more into physics and learn more physics stuff. So I came back for my master's, and now I study scanning tunneling microscopy. Scanning tunneling microscopy, this, first of all, this is the smallest UVC ever written. It's written out of atoms. Each of those bumps is 1 atom. We wrote this by taking a tip, Well, let's how scanning microscopy works first. If you have a tip that's like an atom wide at the tip, and you put it like an atom's distance away from the surface, you get really, really close, you can start sucking up electrons, and you make a current. As you move this tip over your sample, you get a higher current the closer you are to atoms. So by moving it constantly around, you can tell exactly where atoms are. And in doing so, you can also drag atoms around. So by dragging the atoms around, you can make, I mean, this was really just promotional. This is a sort of scientific benefit to running EDC. But that's what we do. And so this is the microscope that I work on. It's in a giant room on a 70,000-ton concrete block supported by these pneumatic pistons that keep it from vibrating in a basement a block up the road here. Because you have to be like an atom's distance away from your sample, it's very, very important. You've got zero vibrations, and so it's in a room that's like cut out from the building in the basement, so it's not touching the outer the rest of the building. So if you've got stomping around in the hallway, you can't feel anything, you can't hear anything. And then the whole microscope itself is supported on these pneumatic pistons that are further isolating it from vibrations. And you've got all these vacuum chambers where you've got no air, no gas or anything, and down into the bottom you've got cooled in this giant thermos filled with liquid helium, and it's just a few microkelvin, millikelvin, not microkelvin, millikelvin. And you end up doing your experiment in a tiny area this big, smaller than a strand of hair, like 100 nanometers, so that's 1,000. That's 100th the thickness of the human hair. So very, very, very small, but it's a big machine to do it. And so that's where I'm at now. I'm in the second year of my master's. I hope to graduate within something like 6 months, done all my courses, and I'm just working on my thesis right now, so it's a very exciting time for me. Do you have any questions? Yeah?
Can you move inside of that room